So, good afternoon. So, do you remember what we have discussed in our last lecture? Is the mic audible? So, what are the topics did we discuss in our last lecture? So, we discussed this algorithm called UCB, and what did we do in that UCB? What was the UCB algorithm? Yeah. So, it, at every time interval, we had an estimate of the arm, which is sample average estimate for each arm. Instead of just relying on the sample estimate, we also added one more term where mu t plus epsilon t, where epsilon t was encouraging the exploration and mu t was encouraging the exploitation, right? So this epsilon t was derived uh, using the confidence intervals that we have. We, with a high probability, we believe that the true mean belongs to this LCB and UCB, right? And with what probability we want the true mean to belong to this interval? How did we calculate that probability? Because we wanted this to hold with certain probability, right? So that we defined something as good event and bad event, right? Do you remember what was the good event? Like for every arm, there is an interval like this in every time slot. So we define good event as the event where our for every arm and for every time, our interval should be correct, right? And bad event as at least in one time slot, our interval for at least one arm should be wrong. So by using Hopting inequality, we know how to calculate these probabilities, right? And we wanted the bad event, uh, like this is how we bound the regret, right? We we bound the regret saying we condition on the good event and we calculate the regret, and then we condition on the bad event and then we calculate the regret. So the total regret, the expected total regret that we'll get is can be written like this, right? Expected, like if you can find number of times an arm A is played, then if you just multiply with NT of A into delta of A, you will know the total regret contributed by that particular arm A, right? So the regret can be written as sum of NT of A into delta of A across all the arms. So we wanted this NT of A, this contribution from the bad event to be negligible, right? At most, the bad event can contribute a regret of t, right? Because we assume the true means lie within 0 and 1, right? So in t time slot, the regret, whatever happens, the regret will not be more than t. So, but we want to make sure that the probability that the regret is more than t is very less. So we want that product, that expected NT of a given bad event into probability of bad to be like order of 1. So we wanted to choose that probability of bad event to be 1 by t, right? So that's how we have chosen our confidence intervals, probabilities for the confidence interval. So we understood that 1 by t cube is a good thing. Then what did we do after that? So we understood what is a good epsilon t to choose. And then what did we do after that? So this is taking care of the bad event, right? By choosing the probability of bad event uh, correctly, we eliminated the bad event. Then what is that we should care about now? In the good event, what is expected NT of A? That's what we need to understand. So in the good event, if you try to look at it, like we just use the basic uh, inequalities, which says that if an arm the UCP of the arm more than the UCP of the if an arm AT if an arm A is played in time t, what do we know? The UCP of that particular arm is better than the UCP of the optimal arm. Otherwise, we will not play that arm, right? Because in every time we are playing the arm which has the highest UCP. So that middle inequality comes from that, and here we just used two other inequalities which says that the good event, we are in the good event scenario. Then based on that, we were able to say that if an arm A is played in any time slot, we are able to see that it's not a the number of times particular arm is played can be bounded by this particular number, which says that if an arm is very bad, what does it tell about delta of A? Arm is bad means the suboptimality is large. That is delta F is large. So if an arm is very bad, then the total number of times that particular arm will be played is at most log T by delta square of A. So a bad arm will not be played too many times. That's what we roughly derived. Now what is that we need to do? Now we have this, we know that in the good event, the number of times a particular arm is played is bounded by this number. Now what is it is left to prove? What is our intention? What do we want to prove finally? What are we doing here in this proof? We wanted to bound the regret of UCB, right? So now we have a bound on this. Can we bound the regret now? So let's try and do that. So we did a brief recap on UCB algorithm, and that in the good event we have derived that this is true in the last class, right? This is what we have derived in the last class in the good event. So now in this class, what we'll do is we'll complete the regret analysis of UCB. So do you remember what is the regret that UCB incurs? Like what is the real proof? So in when we were discussing the ETC, I just mentioned that the best that can be achieved is something, right? Root T, right? So UCB, the version of UCB which we are discussing will roughly have that kind of a bound. So this is the bound which will show. Okay. So it's like root T, but it is off. Like the optimal algorithm will be like root KT, but will be off by a factor of log T, root log. Okay. This is what we'll end up proving. And then uh, I am claiming, right, that the optimal that we can do is root KT. How do we argue that? Like, how do we show that? Because all the time till now showing is showed I've taken an ETC algorithm and showed that it is order of t power 2 by 3 into log something. Then we are able to show that our UCB will incur root KT log t. But if you want to show that any algorithm will incur at least this much regret, how do we show that? Like what we'll look at in today's class. After proving the regret for UCB, we'll try to show that whatever algorithm you come up with, you will incur at least this much regret. That is, that means you tell me any algorithm, I will give you one environment in which the regret will be at least this much, right? Because you cannot say that for every environment the regret will be bad. What if I take my environment where all the arms are equal, like all the arms have equal probabilities of success or whatever, like all the true means are same, let's say. So whatever algorithm you give me, the regret will be zero, right? If I take all the arms have the same true means, then whatever you do, you will have zero regret, right? So the negative results or the lower bounds will be like this. You give me an algorithm, I will give you an environment for which the regret will be at least this much. That is, no algorithm can do better than this for every environment. Okay? So this is called as min-max bounds. We'll discuss that in today's class. These are called min-max lower bounds, which says that no algorithm can do better than this much. Okay. So if like for proving upper bounds, what are the techniques we are using roughly? Like what probability tools are we using for proving that an algorithm incurs at most this much regret? We are mainly relying on concentration inequalities, right? Chernoff bound and Hofding inequality. So what does they typically tell us? Roughly what are these bounds giving us? If you want to be epsilon close to your true mean, how many samples do you need? Right? How many samples do you need if you want to confidently say that you are within epsilon of your true mean, right? It is giving us some sufficient conditions on how many samples do we need so that we are close to the true mean, correct? That's what roughly the Chernoff bound and the Hofding inequality are giving us, right? If you want to be epsilon close to true mean with high probability, roughly how many samples do I need, correct? So these are giving us sufficient sufficiency conditions. But if you want to prove a lower bound, what do we need? We need necessary conditions saying that if the number of samples are less than this much, he will never be close to the true mean. Are you understanding? So we need to show something like you need at least this many samples. Otherwise, you will not be able to probably understand the distribution correctly, right? So we'll look at some tools from probability which will give us some such conditions. Like the concentration inequalities are giving us sufficient conditions saying that if you have this many samples, you can be reasonably correct. We'll look at something called Pinsker's inequality from probability theory, which will give us some necessary conditions. Unless you have this many samples, you are probably going to be wrong. Okay. So we look at those inequalities. There are two inequalities which are called Pinsker's inequality and BH inequality. Just like how we have Hofding and Chernoff for proving upper bounds, these are two inequalities which we'll rely on to prove lower bounds on the regret. Okay. So if your lower bound and upper bound matches, then we call that an optimal algorithm, right? Because any algorithm should incur this much regret, and your algorithm is at most incurring that much regret. So that means it's an optimal, right? So this is roughly the flow of today's lecture. So let's start with this thing. Like in the previous UCP thing, we got this much right. We are able to show that the bad event we already taken care of by choosing the bad probability into expected number of NT of A is order of 1. We have already taken care of the bad event. Now all that we have to take care of is in the good event, what is the expected regret that will incur, right? So the good event at NT of A is less than or equal to this much, right? So the expected regret in good event will be what? Expected regret in the good event is equal to expected value given good into delta, right? So we have showed that whenever good event happens, LT of A is at most that much, right? So we'll have this less than or equal to what? Sigma over A belongs to A. What do we have here? Right? If the if the maximum value itself is that much, the expectation value of that will also be less than that, right? That's the maximum that the random variable can take. So the expected value will also be less than that. So that's all we are using here. So this is equal to what? Sigma over A belongs to A, C log T by delta of A. Correct? So when we are proving regret, so when we say that the regret is upper bounded by something, that means for any environment that should be true, right? Whatever the environment that you take, if you apply UCB algorithm, the regret should be less than or equal to something. So if you look at this formulation, uh, we got some bound on the regret, right? This this regret, it looks like if I have an environment where one of the arms delta of A is very close to zero, right? If I'll take an environment where delta of A of one of the arm is very close to zero, then what is it telling? The regret is very high, like close to like it tends to infinity, right? But we are claiming that the regret should be at most root kt log t, right? So can you can you think of a way where we can use this bond but still be able to prove that bond from here to there? How can we go? Huh? Not audible. AMGM. Okay. So intuitively, what is it saying? The bad arms won't contribute too much to the regret, right? If the arm delta of A is very large, then they won't contribute much to the regret that we know. But what is it saying? If delta of A is very small, then this formula is giving you that it will contribute a lot to the regret, right? But what do we know? If delta of A is very small for a particular arm, what is the what is the worst regret that it can give? Like if delta of A into T, right? It won't be more than that. It won't give infinite regret, right? If delta of A is very small, the regret by the term is decreasing, right? So what we'll do is we'll divide the arms into two categories. We'll look at arms which are uh, good, which are bad. The good arms anyway won't contribute much regret for us because the delta of A of them is very small. And the bad arms, the regret due to bad arms is taken care of by this thing, right? So what we can do is let's divide our arms into two sets, where I'll call the set of all arms, the set of all arms in which I'll take some threshold. I'll call that as delta threshold. If my delta of A is less than some threshold, what is the total sum of all these things can be If I call this as the regret contributed by, uh, I'll define this as, I'll define this particular thing as RTA. That is the regret contributed by RTA. Okay. I'll define that as RTA as regret from me. Okay. This whole thing, I'm calling this as RTA. Okay. So this I can write like this, right? The total regret plus what else? No, so okay. So what we'll do is this particular term. I don't think I want to call this as equal to for this, but this is RTA is the total regret contributed from AME. Let's think of it that way. So then, what will this total sum be less than or equal to for the left? The first term in this will be at most how much? T times delta threshold, right? Correct? Because all the arms in that set are at most having a delta of delta TH, right? So no, then T delta H won't be equal to this, right? This is not equal. Huh? No, like like I think from here we are coming maybe. Like that is one way of bounding it. The regret of any arm that is not equal to that is upper bounded by that. Like the regret, this is an upper bound, right? This is not equal to the regret. So I'm just calling RTA as the actual regret that will incur, expected regret that will incur from army. Okay. So at most this uh, term will come into much, right? The set of all the arms whose threshold delta of is less than delta TH, they can contribute at most T into delta H. Correct? And for the remaining, we'll just use this upper bound which we have. What is the upper bound we have? So if delta TH is greater than something, what can I write? This is less than or equal to C log T by delta TH. I can write delta TH, right? Because delta TH is greater than delta A is greater than delta TH for all of them. So I can write delta TH here. And at most, how many can be there in this summation? Each of them is different. At most, how many can be there? K. We have only K arms, right? Correct? Is this correct? Any arm in that has a delta greater than delta TH. So I can just write the denominator as delta TH. And how many terms that summation can have? At most K. So this is an upper bound, K into that. Now, what is a good way to choose delta TH is, again, you just do some small minimization. We want to minimize the bound, good upper bound, right? So what delta TH will be useful? Can you just quickly try? So so if I choose my delta TH, a good, this is true for any delta TH, right? I can, so I'll choose, okay, I'll choose this delta TH. Then what will I get? What will be left here? C into root kt log t. Yeah? Okay, maybe I took C equal to 1. No? Is this correct? If you don't have that, then what will be left with? Inside the square root. Okay. C. So what is the optimal delta th for this thing? Kc. So here C will be there finally. Okay. So whatever. So it's like order of root kt log delta t. Okay, you can just think of it. Sorry for this. Yeah. So it's like order of root kt log t. Okay. So the main trick is you are just there are multiple ways of arriving at it. I think as one of you pointed out, you can use some standard inequalities like Cauchy squads or something like that to arrive at this. But this is a more intuitive way of coming up with this. Okay, where this is giving us use this form only for arms which are really bad. For arms which are good, we anyway know that the regret is not too much. So we just use that intuition to divide the arms into two sets, and all the arms which are less than some, which are not very bad, they can only which are bad, upper body like that, and then where you should split the good and bad is you just have to look at the expression and decide, and then we are showing that it's order of root kt log t. Okay. So there is some terminology which is useful in the sense that this root kt log t is like the worst case regret that you can incur, right? This is the worst case across all environments, correct? Because for any environment, the regret will be at most this much. Even if you take the worst possible environment, the regret won't be more than this. So that's why this is called a worst case regret bound. Okay. This is saying that UCP algorithm for any environment, the regret will be at most this much. Okay. So this is also called as instance independent regret bound. Instance means you can think of as environment. So instance independent bound, because the bound does not have any term which depends on which environment you are in. Okay. So this is called instance independent bound. Correct? Because it does not have any terms which depend on the environment. Okay. So this is also an even this is an upper bound. So this even this is an upper bound. This is called instance dependent upper bound. Okay. Is this clear? Because it is dependent on the particular deltas that we are having in our environment. Okay. So sometimes using this bond might be good for us. Let's say our environment is such that the arms are very far from each other, like the true means are very far from each other. Then this will give us a better bond, right? Let's say there are only two arms. One of them has a mean close to 0 and the other one has a mean close to 1. Then delta is like 1, right? Delta is like 1. Then we have order of log t kind of a bond. But this is giving order of root kt log t. So if you know the environment and you want to calculate the right upper bound, then this will give us a good upper bound, instance dependent upper bound. If you want a bound which is applicable for all the environments, then this is the worst case bound that we have. Okay. Any doubts till this point? So now that we have seen two algorithms and we got some analysis on the regrets that they'll incur, I want to switch to proving that no algorithm can do better than something. So we'll try to get some lower bounds on regrets. So before that, if you have any doubts, I would like to spend some time and then go on. Huh? No, the algorithm, we are not saying that we know delta when we are running the algorithm. All that we are saying is, while analyzing, we can analyze that. Like the algorithm, the user might not know the delta, but whoever is analyzing the performance of the algorithm, he knows delta. Huh? No, like the UCB algorithm will incur that much regret. You will use the same algorithm which we are using before. So you won't change anything in the algorithm. It's just that if you analyze it for that particular environment, the bound will be like that. Right? You have given UCB algorithm. The algorithm does not know anything about delta. It will just use whatever epsilon t, like root log t by nt of a. That's what the algorithm is, right? Nu bar t of a plus root c log t by nt of a. So the algorithm will just blindly use that. It won't use any information about delta. But if you want to analyze that algorithm on a particular environment, then this is the bound you can give. Okay, fine. Any doubts till now? Okay. So now what we'll discuss is so we want to understand uh, like we want to look at some concept called how do if there are two distributions, how different are these two distributions? If you want to measure that, let's say I have a uniform distribution on 0 to 1. I have some other distribution on 0 to 1, let's say. I want to understand how different are these two distributions. Do you know any measure metric or do you know any way to measure how different are two distributions? Huh? So did you hear about the term called KL divergence? So we look at like just like how we have derived some basic tools before we analyze the ETC and UCB. I'll spend some time on introducing some tools like how we introduce Markov inequality, then Chebyshev, then Chernoff, and then Hopding. We just spent one day on understanding these tools. Then we went on to analyze the upper bounds on regret. Just like that, I'll spend some time on introducing some tools from probability like KL divergence and Pinskers inequality. Once you understand these tools, then I'll show how these tools can be used to derive lower bounds on regrets. Okay. So to start with, we'll discuss this concept called KL divergence. So the KL divergence is denoted like this. Like let's call this. Let's write it as KL. Let P and Q be two distributions. So right now we are assuming it's discrete, so you can think of as PMFs, the probability mass function. Then the KL divergence between P and Q will be defined as okay. So this is just the definition of KL divergence. It roughly gives you how far two distributions are. One like just as a quick check. if you want to see how two distributions are from each other, right? If you take P equal to Q, what do we get? We get zero. So that means KL divergence of P comma P is zero, which is kind of meaningful, right? Because you are trying to measure how different two distributions are. One thing about this is it's not symmetric in the sense that if you take KL of Q comma P, this is not equal to KL of P comma Q. Okay. So these are few properties like KL of P comma Q is always positive. This is one property which we know. And KL of P comma P equal to 0. This we know. And so this is not symmetric. That's why it's not, we cannot call it a distance metric as such, but this is some way to measure how close or far two distributions are. So this is not a distance metric in a true sense, because if you want to call some measure, some function as a distance metric, then it should satisfy symmetry. But this will not satisfy. But it turns out this is a very useful thing, even though it does not satisfy the symmetry property. Okay. If both the distributions are same, then it's zero, right? What is the question? Yeah, they can be equal. For example, if you take two Gaussian distributions, let's say, if I take mu comma 1, like in some cases they can be equal. In general, they won't be equal. That's all I'm saying. Like for example, if you take this, uh, it's symmetric. If you find the KL divergence between these two distributions, it will be a function of mu1 minus mu2 whole square, which turns out to be symmetric. If you take Bernoulli distribution, let's say you have a Bernoulli distribution with probability P1, another Bernoulli with probability P1. If you take another Bernoulli with probability P2, you can find that it won't be symmetric. Okay. For this case, it will be symmetric. Okay. Uh, you can prove it using basic concave property of log. Uh, it's easy to prove. Maybe you can take it as an exercise and prove it. You just need to use the concavity property of log. Okay. So, for those who have taken some courses on information theory, so this is somewhat related to the concept called entropy of an random variable. I don't want to use terminology and confuse you, but for those who know that, then this is also called as relative entropy between two distributions P and Q. You might have heard about this term somewhere in ML or some other place, but this is also called as relative entropy. But you need not worry about the terminology right now. Okay. So I think for this Gaussian case, so this you can take it. You can take this first one as an exercise. Show that the KL divergence is always positive. That is one thing which you can take. The other thing is for KL divergence of so for the continuous case, you just replace the summation with an integral. you can show that the KL divergence will be equal to okay. So I can just give it a try. Okay. So you just need to use the definition of this along with an integral, and you can show that this is equal to this. Okay. So now we get a feel, right? Because it is trying to measure how far two distributions are. If mu1 and mu2 are very close, then the KL divergence will decrease. If mu1 and mu2 are very far, the KL divergence increases. Okay. So now there is inequality called BH inequality, which is also called as a variant of Pinskers inequality, which will be very useful for us to understand how many samples are required to distinguish these two distributions. Okay. So let's say you have two arms. One arm has rewards corresponding to normal distribution with mu1 comma sigma 1, mu1 comma 1, and another arm, let's say, has reward distribution which is normal with mu2 comma 1. So how many samples do we need so that we can distinguish these two arms? Okay. So for if we know this delta, which is the difference between these two arms, how if you want how many samples we need to confidently say that these two are separated, what inequalities do we know? The Hofding inequality, right? So we'll just take epsilon equal to delta by 2. If we take epsilon equal to delta by 2, then we can find how many number of samples are required, so that the true means, if this is mu1, if this is mu2, we want intervals like this, right? They should be separated such that there is no overlap. That is how we derive sufficiency conditions, right? How many samples are required so that you can separate these two things. So if this is what, this is epsilon, right? This is epsilon, this is epsilon. If our epsilon to epsilon is less than delta, then we can separate these two arms based on our confidence intervals, right? So this is by using Hofding inequality, you get some sufficiency conditions on how many n you need so that you can separate these two with some high probability. Now let's state this Pinskers inequality, which will give us the necessary condition. So the Pinskers inequality will tell the following: if P and Q are two distributions, the probability of A plus the probability of A complement in with respect to Q is lower bounded by for any event A. Let P and Q be two distributions which have the same sample space. So for example, if you are taking 0, 1 as a sample space, 0 to 1 as a sample space, so any two distributions on that same space. Okay. So this is telling us P and Q are two distributions. You take any event A, which is a subset of your sample space. Event is what? A subset of your sample space, right? If, for example, if this is your sample space, A could be something like this, which is telling that if I ask probability of A for a uniform random variable, that will be half, right? So this particular BH inequality is telling that the probability of A plus with respect to P and probability of A complement with respect to Q, if you sum these two, this will always be lower bounded by this much. So to just get a quick feel of understanding, if P and Q are same, if P and Q are same, what do we get? What is the lower bound? Yeah. So that bound is satisfied, right? If P and Q are same, what will be the LHS be equal to? LHS will be equal to 1 and the RHS will be equal to half. So this is trivially satisfied. Let's say, can you come up with like P and Q? This is a good case. Like you are, this is the maximum calculated is uh, 1. Can you construct an A, P and Q such that this value is equal to 2? Hmm? So for example, if I take A equal to this, and I'll take a distribution which is uniform between 0 and half. Okay. And I'll take another distribution Q which is uniform between half and 1. Okay. I'll take P is uniform between 0 and half. I'll take Q is uniform between half comma 1. Let's say. Then if I take A equal to 0 half, what is P of A? What is Q of A complement? 1. So this will be 2. Right. But what is the right hand giving us? Like it's we don't know the exact formula for KL divergence, but it will be very like these two are totally opposite. Right? There is no common. Yeah, I'll just write it like that. I'll just say Q is 0 between half 0 to half. I'll just call it a distribution of 0 and 1. I'll just say that Q of 0 for any value between 0 and half, the Q of H is 0. I'll just call it like. Mhm. Actually, to take care of such things, we'll just assume some log 0 by 0 is some 1. These kind of things we'll assume. Or you just take some small epsilon if you want for the remaining probability. So maybe we'll look at the technicality clearly, but roughly, I just want to give a feel of what it is. Okay. Hmm. So, but the right hand will give almost 0 for us because these two are very different. Okay. But this should be true for every A. They should be true for every event A, right? If we take these two as our distributions, what is the minimum that this event can go to? If it's these two distributions, but this should be true for every A, right? That means it should be this inequality should be true even for the smallest LHS. So what is the least value that LHS can take with these two distributions? If I take A equal to half comma 1, what will this value be? If I take A equal to this, then this will be 0. It will also be 0. Okay. So anyway, I just wanted to give you a feel of what this is equal to. So the BH inequality is telling us for every A, this inequality is satisfied. Okay. Now the question is, how do we make use of this inequality to show that you need at least this many samples to separate two distributions? That's our main intention. Okay. Is the inequality confusing? Uh, RHS, why will it change? RHS is not dependent on A, right? No, it could be infinity. Exponent e power minus infinity is 0, right? So that's the extreme case. Hmm. So that inequality will still be satisfied with maybe the KL divergence will be infinity. Okay. Right. So is this inequality fine? All that we are saying is for any event A, they should be true. Okay. Or if this any event is confusing to you, you just write like this. Okay. So this is some matrix. This is some this LHS is a term which depends on P and Q, right? It no more depends on A because I took minimum over all A, right? So LHS is also a term on P and Q. RHS is also a term on P and Q. Okay. So this is just giving us some inequality on these two things. Okay. Huh? Yeah, it will be 0. So LHS was also 0, right? In infimum over all A was what? When you took A equal to half comma 1, we got 0, right? That was the infimum. So what is the doubt? Okay. So this is fine. This is just an inequality. We'll just see how we'll use this inequality to get some lower bounds. Okay. So let's say we have a. So we'll do this thing called hypothesis testing, which is like a term. So let's say you have two distributions. Let's say n of mu1 comma 1 and n of mu2 comma 1. You have two distributions, and let's say you have samples. You have some samples which you are seeing. There are a lot of samples which are obtained from one of these two distributions. You don't know from which distributions those samples came from. You are seeing some samples H1, H2, so on, Hn. Let's say you are seeing some uh, T samples like that, and you don't know from these are taken from one particular distribution among these two. So all these samples came from one of these two distributions, but you don't know from which distribution these samples came from. Okay. Now the task is you want to find out by looking at these samples to which distribution these samples belong to. You want to, it's like a classification problem. You are seeing a lot of these samples. Now you want to classify whether these samples belong to the first distribution or the second distribution. Okay. Now we'll try to make use of the previous inequality to give some bound on if you want to separate these two distributions, you need at least this many samples. If you want to solve this problem, you need at least this many samples. We'll try to use this inequality to get that. Okay. So what will be your natural algorithm? Let's say you see some samples like this. Now I ask you to which distribution these samples belong to. What will you do? What will a natural algorithm? You just take the average of all these samples, and if they are greater than mu1 plus mu2 by 2, you call it. Let's say assume mu2 is greater than mu1, or I'll just to keep things simple, I'll just write it mu. Okay. So if you take the sample average of all these samples, and if the sample average is greater than mu plus delta by 2, you call it the second distribution. If the sample average is less than mu plus delta by 2, you call it as the first distribution, right? This is like the maximum likelihood estimation. So if I want to call this as an event, if I want to define an event based on this, I'll define A as the event where my sample average Okay, is this fine? So whenever the event A occurs, I will assume that I will predict that the samples came from first distribution. Okay, and whenever A complement occurs, I'll say that the samples came from the second distribution, right? Now, uh, we want to understand what is the probability that our prediction goes wrong. Okay, so our prediction can go wrong, right? We'll use this prediction rule, but with some probability, our prediction can go wrong, right? So, what is the probability that our prediction goes wrong? There are two cases, right? Let's say assume that the samples actually belong to distribution one. Okay, then when will my prediction go wrong? If samples came from if samples really belong to distribution 2, when will I, or let's say this really belong to distribution 1, when will I go wrong? When this event happens. I'll call this as P, I'll call this as Q. Okay, this is P, the first distribution is P, the second distribution I'll call as Q. Now, probability of A complement is a probability that I'll do mistake when the actual samples belong to P. Correct? If the actual samples belong to this, then we will mistake, then A complement. Correct? And what is the probability that A complement occurs when the samples come from P? Is nothing but probability of A complement, right? No, that's what I mean. If the samples are coming from that, what is the probability that you'll go wrong? That's what I mean. Wrong given samples are from P. So if you already know that the samples are from P, what is the probability that you will do a mistake? That is equal to probability of A complement, like P of A complement, right? Because the samples came from P, and what is the probability? When will you make mistake? When the event A complement occurs. That is equal to P of A complement. Similarly, if samples actually belong to distribution 2, okay, then what is the probability of wrong given samples are from Q? What is this value equal to? You know that the samples are coming from Q. What is the probability that you will make a mistake? When will you make a mistake? When the samples actually came from Q, what event will lead you to mistake? The event A will lead us to mistake, right? So, since the samples are from Q, what is the probability that we'll make mistake? Q of A, right? Because the samples are actually from Q, and what is the probability that an event A occurs when the samples are taken from Q? Is this fine? So now, what is that we are trying to understand? So we'll try to use this is true for we'll try to use the BH inequality, which is true for any A and any P and Q, right? So we'll take this as our A, and then what do we have? We have that maybe I'll just change the A and A component slightly so that it looks okay. So now we know from Pinskers inequality that this is greater than or equal to half times. So this probability event A, the event A is not a event on one sample, right? The event A, what is the sample space for this event A? Is it about one sample, right? We are talking about what is the probability of A means what is the probability that this sample average is less than or equal to something or greater than or equal to something. So we are talking about probability of n independent random variables, right? It's a probability distribution on the sample space of uh, n dimensional. It's an n-dimensional random variable, right? Because h1 to hn, this is an event on h1 to hn. Huh? No, the samples are random samples, right? Mhm. So the KL divergence, the KL divergence of, so maybe there is a little abuse of notation from me. So here, what we are interested in is the KL divergence between these two. Let's see if I call. Yeah. No, I just changed the definition of A and A from. Right? This is the property distribution of C in this sample. This is the property. They are independent, right? Because these are IID samples. So what we can, there is a property of KL divergence which says that uh, if you have property distribution like this where the samples are independent, the KL divergence between these two distributions will be sum of the KL divergence for each of these samples. So which is like if I define this as PT, like if I define this as PT, which is a joint distribution of these T samples, the KL divergence of PT comma QT is nothing but sum over. So it's just that we know that this product is independent. If they're independent, the probability will be equal to P of H1 into P of H2 into so on. So by using that property, we can show that the KL divergence between these, because these two are not distributions on real spaces, they are distributions on t-dimensional real vectors, right? So the KL divergence between these two distributions will be sum of the KL divergence of the individual Gaussian distribution. Okay, we can show that when they're independent. Okay, and we are having the same distribution everywhere, right? So this will be equal to n times the KL distribution divergence of P comma Q. Sorry, T times. Okay, this is a property of the KL divergence. Okay, is everything fine till now, or is it confusing? Here PTQT. Yeah. Okay. So PT is the joint distribution of T samples of Gaussian distribution mu1 with mu1. QT is the joint distribution of T Gaussian samples with mean mu plus delta. Okay. So now if we use this, what can we say? Probability of A plus Q of A complement is greater than or equal to half into h of, what will be the value here? Minus T into Delta square by 4. Delta square. Delta square by 4. What was the Gaussian thing? It was mu1 minus mu2 whole square by 2. So this is delta square by 2. Correct? Because one was mu1 equal to mu and mu2 is equal to delta. We have told that the scale divergence between two Gaussian distributions with mu1 1 and mu2 2 is mu2 1 is delta square by 2. So this will be t into delta square by 2. This scale divergence between the pt and qt. And what is the LHS for us? LHS is the probability that you do mistake in at least one of these two cases, right? The first case is if the samples actually came from P, what is the probability that you'll make mistake? The second Q of A complement is the probability that you'll make mistake when the samples came from Q. So if the sum of these two is greater than or equal to something, the maths of these two will be greater than or equal to at least this much, right? If sum is greater than something, maths is at least half of that. So what are we saying? In at least one of these two cases, the probability that we do mistake is this much. Correct? This is the probability that we do mistake when the samples actually belong to P. This is the probability that we do mistake when the samples belong to Q. So maths of this is the probability that you will do mistake is at least this much. In one of the two cases, at least you will incur this much probability of going wrong. Okay. So if we want, so so if we have totally T samples, if we have totally T samples, uh, uh, when can we say that there is non-zero probability of making error? Like the probability of error will not will be a constant. At least with some constant probability, you will make error. Like generally, we want the probability of error to decrease with t, right? As t increases, we want the probability of error to decrease, right? Because as you observe more and more samples, you want to be sure you should be able to distinguish these two distributions, right? But if I choose my delta to be a function of t, right? If I choose delta equal to, let's say, delta less than 1 by root t, or like roughly 1 by root t, if I choose my delta equal to 1 by root t, how many hours, how much ever I increase my t, the probability of me making an error will not decrease. Correct? If I choose delta equal to 1 by root t, what is the probability of making error? It is some fixed number which is independent of t. So that means if my means are very close, irrespective of how many samples I take, I'll never be able to distinguish those two distributions with zero probability. Right? My probability will be constant. It will not decrease with t. So I can keep increasing my samples, but if delta becomes smaller and smaller, I'll not be able to distinguish these two distributions. Right? No, delta for Gaussian I'm talking about. Delta is this, right? So what is the question? All that we are saying is we know these two distributions. We know this mu and mu plus delta, let's say, and you are seeing some samples from one of these two distributions. Let's say you have some samples. You want to classify whether this belongs to, let's say, mu equal to 1, let's say, and you want to classify whether this belongs to n1 comma 1 or n1 comma, let's say, delta is equal to 1, n2 comma 1. So you know this. If, let's say I assume you know that. You want to classify whether they belong to this or that, because our event itself depends on this. If you don't know what delta is decided, you are saying that if the average belongs to is less than mu plus delta by t, you declare this as distribution uh, 1, otherwise you declare it as distribution 2. So here in this particular example, we know what are the mu and delta. But even if you know that, all that I'm saying is if your delta is small, or if your delta decreases along with one as a function of t, how much ever you increase your t, there is a your probability of error won't decrease. No, in the worst case bounds, what is our delta? In the like we just discussed instance independent bounds, right? In our UCB, that means it should hold for any delta, right? No, if you want to give some worst case guarantee, you are not saying that my algorithm will work only when my delta is this much. If you want to say that irrespective of what my environment is, my algorithm is going to have this much regret. So you want instance independent bounds. So for that case, if your delta can be arbitrarily low or high. For every delta, whether your algorithm will work or not is what the instance independent bound telling you, right? So this root t regret essentially comes from this roughly from this intuition. Okay, if your delta is 1 by root t, there is a lot of we have to make it more precise, but roughly the root t regret comes from this. If your delta is roughly 1 by root t, the regret will be delta t, which is like root t, like 1 by root t into, like your regret will be t into delta. If your delta is chosen badly like this, so you will roughly have root t regret. Yeah, we have to make that very precise in our bandit setting, but everyone understood this much, right? If your delta is very small or decreases with as 1 by root t, how much ever you increase your t, your probability of error won't go to 0. It will be a constant probability. Okay, based on this, we'll derive the regret lower bounds. Okay, thank you.